Hello, everyone. So we're going to pick back our discussion of waves, and we're going to start today by talking about energy transported by waves. So we know that there must be some energy driving this wave motion, right? We have forces that are doing work on objects to cause oscillations, which are driving the waves. So there has to be some energy that is being transported by the waves, right? So if we have some wave here traveling along, and we consider some little kind of box of the material here, so let's say we've got this kind of slab of material. Something like that, and the wave is traveling through this particular slab of material, and let's say the area of this surface we're going to call S, and this length here is going to be L. And of course we know that L is going to be the same as the speed of the wave times the amount of time it takes for the wave to travel through that particular section, right? So we will start out there, and again this wave is traveling here at some speed v. Okay, so as this wave travels through here, say we have a transverse wave, then we know that particles are going to be moving up and down in a simple harmonic motion, right? And we know the energy associated with simple harmonic motion is going to be 1/2 this k, this kind of force constant there, times the amplitude of that oscillation squared, right? So that was what we've shown already back in chapter 14. We also showed that omega, the angular frequency of the motion, is equal to k over m, and that this is also then equal to 2 pi times the frequency, right? So from this equation here, we can solve for k. So if we square both sides, we get k over here. We're also going to be multiplying by m. So we have a 4, we have a pi squared, we have an m, and then we have a frequency squared, right? So that is our spring constant, quote unquote. And we can plug that in to our energy equation over here. So the 1/2 and the 4 leave us with a 2. We get pi squared mf squared. And also a squared. There we go. So that is the energy being carried by this wave, right? So if we have some three-dimensional wave, say, traveling in an elastic medium, then the mass is, of course, just the density of the medium times some volume. And in this case, our volume is going to be this surface area times L, right? That's our volume. And we have some density rho. So we can also say that this volume is going to be the surface area, the speed of the wave, times time. So from here, then we can say, well, if this is our volume, then the mass is just the density times the volume. And so we can take that the mass then is this going to be this density times the surface area S times the speed of the wave V times time. And so then we can plug that into our energy equation here. So we have rho S V T F squared A squared. Okay. So this is then the energy that is being transported through that volume of material over time. And so if we wanted to then go back and recall, well, average power was just the energy divided by the time. So if we divide this equation here by time, right? So E over T, that's going to leave us with just the 2 pi squared rho SV F squared A squared. Okay. So one thing that we do want to note here is that the energy transported by a wave is proportional to the square of the amplitude, right? So here's the square of the amplitude and the square of the frequency. Right? So that's how the quantity depends on those two things. And so what this would then mean is, for a small increase in amplitude, you're going to get a larger increase in energy. All right. So we have one last thing. So this is our average power in the wave. And then we have this quantity that we define as the intensity. And the intensity then is going to be the average power transferred across a unit area perpendicular to the direction of energy flow. So it's basically this power per area. So we give it the symbol capital I. And we have the average power divided by our surface area. And that, of course, is going to be 2 pi squared rho V F squared A squared. Okay. All right, so if we have a isotropic medium, meaning that the medium is the same in all directions, and the wave is originating from a point source, then we get spherical waves. And so we can kind of draw a little picture here. So let's say we have some point here, and that point can be thought of like, say, a speaker sitting in the middle of a room. That is going to be sending out waves in kind of all directions. And so we get around this, you're going to have these kind of compression, rarefaction and compression rings around this, and they're going to go out in this spherical manner. And so the area that the energy is being transferred across is going to be given by the surface area of a sphere. And so the surface area then is 4 pi times the distance from our source squared. And so this would then mean that our intensity is the power over S, which is the average power over 4 pi r squared. Okay. So if our power output is constant, then the intensity is, of course, going to decrease as 1 over r squared, right? So jot this down. If this is constant, then our intensity is just proportional to 1 over r squared. So this is what we generally refer to as an inverse square law. We've already seen an inverse square law when we studied Newton's universal law of gravitation. That was also an inverse square relation. So what this means is if we consider 2 points that are different distances away from the source, right? So we have consider 2 points, R1 and R2. Then we can look at this ratio of intensities, right? So we can say the intensity at 2 is going to be this average power divided by 4 pi r2 squared, and then we have our average power divided by 4 pi r1 squared. And so a lot of these things are just going to cancel each other out, right? So if we have constant power output, then we have this 4 pi's are also going to cancel, and we're left with r1 squared over r2 squared. So this then tells us how the intensity kind of drops off with distance, right? So we can see that if you say have some distance that doubles, so if R2 over R1 is 2, then the intensity is going to be 1/4 of its earlier value. So it drops off very rapidly with distance. Okay. So one way that you can think of what's going on here and why the intensity has to drop off this way is if you are putting out a certain amount of energy per time, then that energy is propagating outward and you still have that same total amount of energy, right? You can't create or destroy the energy. Energy is conserved. So you have that same amount of energy, but it's being spread out over a larger and larger surface area. So the intensity has to then drop off inversely proportional to that surface area. And this will happen even if you have a medium where you don't have any kind of dissipative forces acting on the material. So if you have no forces between the particles of the medium, then you would have no dissipation, but you would still have the energies being spread out over a larger area, so the intensity has to drop off. Okay, so this also then means that the amplitude of the wave is going to decrease with distance, right? So we know that the intensity is proportional to the square of the amplitude, right? We wrote down previously that our intensity here, we had a bunch of constants out front, but we'll just say that it's proportional to the amplitude squared, right? So we wrote that down back up here. And so as the amplitude, or sorry, as the intensity is dropping off, so is the amplitude. So we can say that the amplitude is going to be proportional to the square root of the intensity. So it's proportional then to the square root of 1 over r squared, which is equal to 1 over r. So the amplitude is just going to fall off directly with distance instead of as distance squared. Okay. So if we have constant power output, then we can again do something similar to what we did up here. We can say, well, we have some area S1 times our amplitude A1 squared is going to be equal to the area S2 A2 squared, right? Where these A1 and A2 are going to be the amplitudes of the waves at position R1 and R2, and our S1 is going to be 4 pi R1 squared, and S2 is 4 pi R2 squared. And so if we make the appropriate substitutions here then, right, so we have 4 pi R1 squared, A1 squared is equal to 4 pi R2 squared, A2 squared. 4 pi's are going to cancel away. And we can again kind of solve for the ratio. So I can move this A1 over to this side. We can move the R2 over to this side. We can take the square root of everything because everything is squared. And we're going to get A2 over A1 is going to be equal to R1 over R2. Okay, so this is giving us then a relation between amplitude at one point and amplitude at another point. So if you were, say, given the amplitude of the wave at some R1 and then asked what it would be at R2, you could use this simple expression here to solve that, and we could use our expression up here to find the intensities as well. Okay, so now let's consider an example here, and this is the earthquake intensity example in the textbook. So we have the intensity of an earthquake P wave traveling through the Earth detected 100 kilometers from the source is 1 times 10 to the 6 watts per meter squared. We want to know what is the intensity of the wave if it was detected 400 kilometers from the source. And so that's where we're going to use our expression up here. So we have that I2 over I1 is equal to R1 squared over R2 squared, right? So what we want is effectively we're going to be solving for I2. So I2 is R1 squared over R2 squared times I1. And so now at this point, it's a relatively straightforward example. We were given the intensity here, that was 1 times 10 to the 6. We know that R1 is 100 kilometers and our R2 is 400 kilometers. So all we have to do is plug in the numbers. And whenever we have these kinds of ratios of distances, it doesn't matter. You don't need to convert your units because you're going to be dividing one by the other and the units are going to cancel out anyway. So the ratio of two lengths and any units should be the same regardless of what those units are. So as long as these two things have the same units, we don't have to actually convert between any of those. So we have our 100 kilometers squared over our 400 kilometers squared times our 1 times 10 to the 6 watts per meter squared. And when you plug in all of these numbers, you should get 6.3 times 10 to the 4 watts per meter squared. So we can see that the energy has indeed fallen off quite a bit. The intensity there should be something like 1/16, I believe, of the original, because when you square something that's like 4, you're going to get 16 on the bottom there. So falls off quite a bit with distance, and that's because of that inverse square relation. So if we are talking then about a one-dimensional wave, then it's a bit different, right? So the area is going to remain constant, right? So if you have a wave on a string, we don't have the area changing, so that area stays constant. And so that means that the amplitude is going to stay constant. And if the amplitude stays constant, then we won't see any drop in intensity. So for a one-dimensional wave, the surface area is constant. So if our power output is also constant, then our amplitude is constant and our intensity is also constant, right? So that is just if we go back and we look at all of these equations up here. So if this S is a constant and P is a constant, then intensity has to be a constant. And if intensity is a constant, then the amplitude has to be a constant over here. So that is what will happen if we have a one-dimensional wave. But in practice, there is going to be some sort of friction involved here, and so that's going to cause a damping in the motion, which means that you will have some of the energy that is being transported along the wave being converted into heat, and then that heat is going to go away, and so you will see a reduction in amplitude and intensity even in a one-dimensional wave. So in practice, we have to worry about friction, and so then that means that both the amplitude and intensity decrease, and that's because our friction is converting energy into heat. So we do have that loss of energy, and so again, if we go back and look at some of our earlier equations here, If you have a loss in energy, if energy is decreasing with time for any reason, then amplitude has to be decreasing with time. And if amplitude is decreasing with time, then the intensity has to be decreasing with time as well. Okay, so now we want to discuss a mathematical representation of our waves. So up until this point, we haven't really actually written down an equation for any of our waves. So this is going to be our mathematical representation of a wave. Okay. So we're going to label this as a capital D. So this is going to be our displacement function. So kind of how far displaced from the equilibrium position is any particle given its position in space. And we can see that if we have, say, a snapshot of a wave at a particular time, we have this kind of sinusoidal shape. And so we can say that's going to be some amplitude A times the sine of 2 pi over the wavelength. And so sine waves and cosine waves, they have this kind of inherent 2 pi to their period, right? So 2 pi gets you all the way back to where you started from. And so if we take our wavelength, if we take that 2 pi and we divide by our wavelength, and then we multiply by some position x, then that will tell us how far from equilibrium that particular point should be displaced, and it will be in terms of this total overall amplitude, right? And we will switch over here and take a look at a plot of a wave. And so the solid curve here is going to represent our wave at t equals 0, and the dashed curve represents our wave at some later time t, right? So we don't need to worry about a specific value there, but that must be the case. So this, again, this is our displacement, and A is still our amplitude. And we can see if we just look at that t equals 0 curve, right? So then it's described by the equation that we just wrote down, that amplitude times the sine of 2 pi lambda times x, right? 2 pi over lambda times x. And we have all of the kind of usual characteristics that we've seen before, right? So the distance from one point on the wave to an equivalent point, that gives us our wavelength. And we have the amplitude is kind of the highest or lowest away, furthest away from that equilibrium point, right? So the same characteristics we've dealt with before. Now, if we do consider that time t later, then this wave will have traveled, right? So by traveling, again, we can kind of go back. Let's see if I can switch over here. So here was our traveling wave that we looked at last time, and you can see that this peak is moving to the right over time, and as time goes on, it moves further and further over. So back to this static picture here, and so after some time t, this will have moved some distance where we take v, the speed of the wave, and multiply it by that time. And so now we need this x position here. So we had some x here where we had this maximum position. And then we need this new point over here, this new x, to have that maximum value. And so we need to take this x position here, where this peak is going to be at that later time, and we need to subtract from it this distance vt to get back to this point, right? Because then that would have that same value. So if we go back to our whiteboard here, so what this means is that at some time t, our displacement equation should be written as the sine of our 2 pi over lambda times x minus vt, right? Because we need to shift the argument of our sine function back to where it was at t equals 0, so that at this new x position, we get that same maximum amplitude or whatever displacement we had at a previous x value. Okay, so this then is our function for describing a wave that is traveling in time. And so then if we go back again, let's see, switch over here. So here was our static diagram, and we can switch over. And so then this is the kind of equation that would describe this blue curve that is traveling. So that's our traveling wave, and it's described by the equation that we have right here on our slide. So this one right here. Okay. So we can write this particular equation in different ways. And so the first thing that we can do is we could just distribute this 2 pi over lambda. So we would have a sine, we have our 2 pi lambda x, and then we have minus 2 pi v over lambda t, right? But we can then recall that the speed of a wave is our wavelength times our frequency, right? So we can plug that in, and we can say, well, this is sine 2 pi over lambda x minus 2 pi lambda f over lambda times t. That lambda is going to cancel away, and we have 2 pi lambda x minus 2 pi f t. But of course, our frequency and our period are just the inverse of each other, right? So we can then re-express this as a times the sine of 2 pi over lambda x minus 2 pi over the period t. Okay. And we can also make a few other simplifications here, right? So looking back here, we know that this was defined as omega. This is also omega, that angular frequency that we talked about when we discussed simple harmonic motion, right? So that's in there. So we can replace this 2 pi over t, or the 2 pi f, with just this omega. And we can define a new constant, or a new variable. Well, I guess it is, in a sense, it's going to be a constant for a fixed wavelength. And that is what we call the wave number. And the wave number, we use the symbol lowercase k, and that's going to be 2 pi over the wavelength. And so this is where things can get a bit confusing, because we were using previously k to be the spring constant, and even within this chapter itself, we've used k to be this kind of force constant for these Hooke's law type forces. But this k is the wave number, and it is very different than that spring constant. So it is important to try to keep these things straight in your head. So here, with those definitions, we can then have kind of the simplest way to write our wave equation, which is just k times x minus omega times t. And so again, be very careful here. This k is the wave number. This is not the spring constant. Okay. So we can also then describe a few things here. So this k x minus omega t here. This is what we call the phase of the wave. And so the speed of the wave, or the velocity of the wave, we'll say velocity of the wave here, is called the phase velocity. And we can define that wave velocity in terms the phase velocity in terms of this angular frequency and the wave number, right? So since our wave number is 2 pi over lambda, that means that our wavelength is 2 pi over k. And since our frequency is equal to, well, I guess we'll do it as omega is equal to 2 pi times the frequency. So then the frequency is omega over 2 pi. And again, we know that for any wave, we can write that the speed is going to be the wavelength times the frequency. So this is 2 pi over k, just using that, and then multiplied by omega over 2 pi. 2 pi's cancel, and we get that the speed of the wave is this angular frequency divided by the wave number. So this is our angular frequency. And this is our wave number. Okay. We can also see what would happen if our wave was moving in the opposite direction. So let's just go back and look at our picture here for a second. So when our wave was moving to the right, we saw that the distance that the peak traveled in some time t is going to be the speed of the wave times t. And so to get a peak value of our displacement function at this point x, we had to subtract out this distance vt from this new x to get back here to get the same amplitude that we had at that point. Now, if the wave was moving to the left, we would have the same kind of argument, but now you would have to add in the value, right? So if this is our starting position here and our ending position there, this position you would have to add this distance vt so that the argument of your sine function was that same value again, so that you would have the same kind of overall displacement at that point. And so for wave traveling to the left, then we would write that our displacement as a function of position and time is equal to our amplitude sine times our 2 pi lambda x plus vt. And we can go through the same kind of arguments that we did before, and we can express this in multiple ways. So we have this equation here, 2 pi over a period times t. And of course, we have the simplified version, kx plus omega t. And so we can write in general, our displacement equations have the following form. So we're just going to write the simplified version here just to save some writing. Now, plus or minus omega t, where the plus case is wave moving left, and the minus case is the wave moving to the right. Okay, so that is how we describe a wave that is moving. And so we can examine this in a little bit more detail here. So let's start with our wave moving left. And this is just because then we don't have any minus signs to deal with. Though it would still work out if we did have those minus signs to deal with. It would just be a little bit more difficult to see directly. So if we look at this at t equal to 0, right? So then we get d of x and 0. This is going to be equal to a times the sine of kx, right? So that's our t term just drops out. Now, if we look at the wave shape in space at a particular time t1, some later time, then we would have, so at t equal to t1, we have d of x and t1. It's going to be a sine of kx plus omega t1. Right? So we can see here that we have this kind of sine wave. And if we took a picture of the wave at this t equal to t1, we would see this sine wave where we have some phase constant omega t1, right? So for a fixed time, the wave has a sinusoidal shape in space. So for fixed time, wave is sinusoidal in space. And if we then said, well, let's look at a particular point, right? So let's look at x equals 0 at any given time. So we have d of 0 and t. Then in that case, we just have a sine omega t, right? And this is just the equation for simple harmonic motion. So this is simple harmonic motion. And so if we look at the wave at a fixed position, then we have just simple harmonic motion, and it can differ by some constant, right? So then if we said at some x equal x1, and we have d of x1 and t, we would get a sine omega t plus kx1. So again, we just have this kind of phase constant here. Okay, so we can also say that in general, we can have an overall phase constant or phase angle. And this serves the same purpose that it did when we looked at simple harmonic motion. So our particle displacement as a function of position and time can be kx minus omega t plus some constant phi, some phase angle phi. And so this, again, like I said, it serves the same purpose that it did in simple harmonic motion. And that was to account for the shape of the wave given certain, the motion given the initial conditions. So this adjusts, so our phi adjusts for the shape of the wave at t equals 0 and x equals 0. So whatever the initial conditions of the wave are will determine the value of phi. And so if we go back again to our kind of simple little diagram here, so this solid curve here, we can see that at if that was at our t equals 0, which is what we said it was, our x equals 0 value then is also 0. And so that would give us a phase angle of 0. But the other wave in that diagram we have is shifted away from that. So we would have some phase angle then to describe that shape of the wave at x equals 0 and t equals 0, right? So if that was our initial wave, then we would need some phase constant to shift everything for us. So everything we've talked about so far is just for sinusoidal waves, but we can have wave pulses that take on a variety of different shapes that are not necessarily sinusoidal. And in particular, these kinds of wave shapes are going to show up in a lot of like electronics sorts of applications. So when you're applying voltages, you can have varying voltages over time, and those voltages can vary as sine waves, or they can vary as what we call a sawtooth wave, or a triangular wave, or a square wave. So we can have these different shapes. So we have our kind of, usual sinusoidal. You can have square waves, which just kind of jump between two extreme values. This would be our square wave. We have a sawtooth wave where you have like this increase followed by a drastic drop, a rapid drop back down, and then increase back down, and so on and so forth. So it looks like the teeth of a saw. That's our sawtooth wave. And you can, of course, have a triangular wave where you go kind of slowly, nice and uniformly between two extreme values like this. So that's a triangular wave. So all of those are different shape waves that we can have, but they can all be described very similarly. So they will have different functional forms, but we will still have that our displacement at some given time. So at x equals 0 is going to be, whatever the initial shape of the wave is. At some later time, you would have x and t. And this is still going to be described by kind of a function of x minus vt for moving right. And we're going to have d of x. Oh, and I forgot to switch back over. Sorry about that. So again, what I was saying is that we were looking at things purely in the terms of sinusoidal waves, but we can have similar equations for any shape wave. So we have the square wave here. Again, that's just going back and forth between kind of extreme values. So you start at one extreme and then very quickly go to the next and back and forth. We have this kind of sawtooth wave where it's kind of a gradual rise in something and then drops off. Again, gradual rise, drops off, and so on and so forth. So it looks like the teeth of a saw. And then you have a triangular wave, which would be kind of a nice linear rise in value, then followed by a linear drop off at the same rate, and then back and forth. And so we can write our functions, whatever they are, they're going to be very similar. They're going to have the same kind of dependence on x and t. So we get to these expressions here. So if the wave is moving to the right, it's still going to have an argument that's like x minus vt. And if it's moving to the left, it's going to be like x plus vt. Okay. So let's look at an example, and then that will probably be it for this particular lecture. So we have a traveling wave So the left-hand end of a long horizontal stretched chord oscillates transversely in simple harmonic motion with a frequency of 250 hertz and an amplitude of 2.6 centimeters. We're told that the chord is under a tension of 140 newtons and has a linear density of 0.12 kilograms per meter. At t equals 0, the end of the chord has an upward displacement of 1.6 centimeters and is falling. We want to first determine the wavelength of the waves produced and then find the equation for the traveling wave. Okay, let's write down some of this information that we were given. So we have simple harmonic motion, which had a frequency of 250 hertz. That's kind of our driving frequency. We were given that the amplitude of those oscillations were 2.6 centimeters. We were told that the force of tension is 140 newtons. We were told that the mass density here is 0.12 kilograms per meter. And let's see, at t equals 0, the left hand, right, the end of the chord has an upward displacement of 1.6 centimeters. So at t equals 0, we have that d of x equals 0 and 0 is going to be equal to 1.6 centimeters. Okay, so that and that it is falling, so it is on the edge of the wave that is moving down. And so we're going to need that to find our phase constant in the end. But the first thing that we want to do in part A is find what is the wavelength of the waves. And so for that, we have to recall that our wave speed is our wavelength times our frequency, but it's also, for a chord, going to be the force of tension over our mass density. And so then this tells us that the wavelength is equal to 1 over our frequency times the square root of our tension force over that linear mass density. And so now we just need to plug in the appropriate numbers there. So we have a 250 hertz for the frequency. We have our 140 newtons for the tension. And then we have our 0.12 kilograms per meter for our mass density. And this will then give us a wavelength of about 0.14 meters or 14 centimeters. Okay, so that is the wavelength of those waves. So now we want to write down an equation to describe the wave, the traveling wave. And so we're going to start by just writing down our general equation, right? So our general equation tells us the amplitude times the sine of kx plus or minus omega t plus phi. Right? So we need to find some of these values then, right? So we need to figure out what is k, what is omega, and what is phi. And our amplitude we're just given, right? So that's just the 2.6 centimeters. But we need to find the other values. So for the wave number, we know that that is 2 pi divided by the wavelength. And we just found the wavelength. So we have 2 pi over our 0.14 meters. And so that is going to come out to, let's see, about 45 meters to the minus 1, approximately. We know that omega is 2 pi times our frequency, and so we have 2 pi times our 250 hertz. And so that comes out to 1,570 inverse seconds or radians per second if you want for the angular velocity there. And then we need to find our value for phi here by using our expression that we had previously. So we have that we have 1.6 centimeters is going to be equal to our amplitude of 2.6 centimeters times the sine. Well, I guess let me write out a couple more details here. So we have d at x equals 0, t equals 0, right? So when we look at our equation up here, if we set x and t to 0, both of those terms drop out. And so this is just going to be equal to a times the sine of phi. And we know that in this particular case, that's going to give us 2.6 centimeters sine phi equal to 1.6 centimeters. And so if we divide both sides by 2.6 and take the inverse sign, then we can get phi, right? So we have sine inverse of 1.6 centimeters over 2.6 centimeters. And again, since we are dealing here with a ratio of distances, as long as their units are the same, it doesn't matter what they are specifically. And so if we take this inverse here, this inverse sine of 1.6 divided by 2.6, then we get that this is 38 degrees, which is also 0.66 radians. And then once we have all of the appropriate values, it's just writing down the equation. So we can write this as 0.026 meters times the sine of our k, 45 meters to the minus 1 times x. And then if we are moving, I think it said the left-hand end up and down, then our wave is going to be traveling to the right. So we have a minus sign here. Then we have our 1570 times t. So that's our 1570 radians per second t. And then we have plus our phase angle, the 0.66. So then that is our equation for this traveling wave. So next time we will finish our discussion here of wave motion and then probably move on to starting our discussion of sound waves, which we treat specially because they have some special properties to distinguish them from other waves. So we will pick up with that then. So I will see you all in the next one.